Here we're talking about the properties of waves, and I want you to imagine just a little thought experiment. Imagine you're in a pool and there's a floating ball kind of beside you, let's say it's there, and either you make the waves or somebody else does a cannonball into the pool or something, and there's these big waves, and you watch the motion of the ball. And I want you to imagine, how does the ball move? So you can kind of close your eyes and imagine that you're floating in a pool, there's a ball nearby. It's going to look something like this. Okay, so here's the waves. You can kind of see the wave. Where's my laser pointer? There it is. So here you can kind of see the wave, right, as the wave is moving along this way. And if you can imagine right over here, one little particle, imagine that's like the ball. The ball is going to move up and down. So as the wave moves to the right, again, I can kind of point on it if I can get my little red dot here, right? I can kind of point to the crest as it moves to the right. But notice how one particle just goes up and down. There may be, if you've actually been in like the ocean or a lake or something like this where there's a ball floating, it may also go a little bit forwards and then come a little bit backwards. Sometimes there's a bit of circular motion, but sometimes you ask, like, what is a wave? The wave is not the water, because you can have water without a wave. A wave is a disturbance that transfers energy through a medium. The medium in this case, in most cases, the medium is like water. It could be other things. Air can be the medium that sound waves travel through, but let's imagine water waves. In the case of water waves, the medium is the water and the wave is just the disturbance that goes through it. You can kind of see, you can kind of see again from this diagram up here, or this little animation, the wave is moving to the right. But look at the individual particle, the little particles. You could pick another particle if you want, but that one particle there just kind of goes up and down. The medium does not move. Another example of it would be like people doing the wave. You maybe have been at a stadium or something where the wave is going. If you look at this wave, the people are the medium. The disturbance is them kind of going up and down. But if you look at one person, like pick this person right here, they don't move to the right or to the left. They go up and down, but they don't move to the right or the left. But clearly you can see that the disturbance kind of, if I point along with it, the disturbance kind of goes to the right. Okay, so the wave is the disturbance. The medium is the people. The people aren't running to the right. They're just kind of going up and down. A real kind of more complex water wave looks more like this. And you can see where up at the surface up here, you can see this guy right here, the blue one. It kind of moves more around in a circle a little bit. The farther down you go, the less they move, which is why most fish and whales and stuff, they don't mind when it's a stormy day out in the water. They just go down deep and then it's all calm down there. All right, let's talk transverse waves. The crest is the max position above rest position. The trough is the minimum. So rest position is kind of this dotted line. If you had like a rope and you stretched it out, maybe an elastic band or something, and you stretched it out, there's the rest position. But as you kind of like flick the end up and down or something, it's going to go like up like this. Probably a little bit later it'll come down. This spot over here is going to go up and down. If we wanted to talk about crests, the crest is the maximum position above rest position. So right there is a crest. Right here is a crest. The trough, this word is trough, like a feeding trough, I guess, an animal might eat out of. That's below the rest position. So right here is the trough. We can only see one here, but you can imagine like a nice sine wave. There's probably another one over here, maybe another one off to the left somewhere. The wavelength is from crest to crest. Or you could go from trough to trough. Again, we don't see the other trough over here, but you can imagine it's out there. Or really from any one position to the same position when we're kind of heading in the same direction. So you can kind of imagine right here, we're kind of going like down to the right. Here we're back at the same position, but we're going upwards over here. So that's not one wavelength from here to here. One wavelength would be from here all the way over to here, where we're again coming back down. Wavelength measured in meters. Of course, you can measure in centimeters or kilometers, but our base unit is meters. That is a transverse wave. On the other hand, a longitudinal wave is this kind of a wave. So imagine you stretch out a slinky between two people, and the person over here kind of moves their hand forwards and then brings it back. As you move your hand forward, you're going to compress the coils of the slinky closer together. That's what they're talking about here. Okay, if you don't know what a slinky is, it's like a spring or something. And the compression is where it's like it's compressed together. Okay, we've kind of squeezed those coils tighter together. Whereas a rarefaction is when the coils move farther apart. Right in here or right over here is a rarefaction. That's where they are, it's like they're more rare. The coils have moved farther apart, so there's less of them in a certain area. There's just some fun facts. Notice the reflection from a fixed end versus a free end. One kind of stays on the high side, like this one down here. Whoa. There we go. This guy comes on the high side and reflects back on the high side. This guy reflects on the opposite side. Normally, I would take you outside, out into the hall, and we'd stretch out a long slinky and try this for real. So don't worry too much about this, but an interesting thing to notice. The universal wave equation. Normally I'd have some music playing here. Universal wave equation right here. It's a big name for a small equation. If you remember, V is displacement over time, or distance over time if you want to talk about speed. For waves, the specific time that we're going to talk about is the period. It's a time for one cycle. That's capital T. And the distance that we're going to talk about, the specific distance, is going to be for one wave. That is the wavelength. If I remake those replacements, I get this. And frequency is 1 over period, so I get this. I'm never going to ask you to derive this equation, but there is the universal wave equation. It really stems from just this old equation that we know from way back at the beginning of the semester. So universal wave equation. I can't remember if I said this later, but V is just speed of the wave. F is frequency of the wave. Lambda, that symbol right there is lambda, this symbol. Lambda is wavelength. And just for units, speed, meters per second. Frequency is hertz. Wavelength is, whoops, that's meters. There. Let's try this thing in an example. So we've got a speedboat. I don't know if I'm going to be able to draw a speedboat, but let's just kind of imagine. Here's a some kind of a speedboat or something. There's some windows in the front. Here's the water level. I should do blue, I guess, for water. Here's the water level. Somewhere over here, we've got a person swimming. So they're kind of like this. There they are. That's not bad, eh? Person swimming. The speedboat is going to make some waves. Okay, so the waves are going to be like, here's a wave, and it's going to travel this way. As those waves travel, you kind of know they're going to sort of do this thing up and down, up and down. I won't cover the swimmer with them just so we can see them. The speedboat passes 45 meters away from the swimmer. That's a distance. Okay, it's nothing to do really specifically with the wave. It's just how far away, how far the waves have to travel. The first waves reach the swimmer 4.5 seconds later. So the time it takes for the wave to get to the swimmer, 4.5 seconds. But we also know something here specific to the waves, the distance between two successive crests. Okay, successive means side by side. So here's two crests side by side. The distance in here from this one to this one is 3.5 meters. That is lambda. Okay, so we could say over here, lambda, 3.5 meters. The distance between two successive crests is the wavelength. And then the question is asking me for what's the frequency of the waves. In order to use this, I would like to use the universal wave equation. That means I need to know what is V. Over here, on this side over here, I just happen to have enough information to solve for V. Oh man, I don't know why my red dot, there it is. It's tricky to bring that red dot out. What I know is speed is distance over time. So as one of these crests comes out from the boat, it takes 4.5 seconds for it to travel the 45 meters to the swimmer. That means I can find the speed of the wave. The distance is 45 meters, time is 4.5 meters. That looks like something easy I can do in my head, but I'm going to use my calculator to double check. 45 divided by 4.5, yeah, 10. Seemed too easy, you know? The speed of the wave is 10.5 meters per second. That is also the speed of the wave over here. It's the same wave. That means I know that the waves travel at 10 meters per second. Frequency, I don't know, but I do know the wavelength is 3.5 meters. Okay, so I can take that 10, divide by 3.5, and the frequency then is 2.857. We want 3 sig digs, actually 7.1. We want 3 sig digs. We're going to cut it over here, so 2.86 hertz. Frequency is measured in hertz. Hertz actually is inverse seconds, 1 over seconds. Kind of a weird unit, but frequency measured in hertz. And that's it.